Understanding physics, hard bits. This video is about exponential functions. What's that then? Well, now this is really basic stuff I'm going to start with. And if you do A-level maths, then hopefully you'll be saying, why is he going on about this? This is ridiculously easy. But I want to start from the basics. I want to get more and more tricky as we go along, just to make sure that there are no gaps. Okay, now what is a function? Well, a function tells us how one variable changes when another thing changes. So if we look at this, y is a variable, x is another variable. In this particular equation, k is just a constant. And basically when x changes, what happens to y? So we say y is a function of x, yeah? And that means that the value of y depends on the value of x. Y is a function of x. And x might actually be time. So y is a function of time. So as time passes, y changes, yeah? Y is a function of time. Pretty basic stuff. Now look at these. I've got these functions on the left hand side and I've got all these graphs. What I'd like you to do is pause the video and match them up. See if you can recognize the graph that goes with these different functions. So pause the video now and I'll tell you the answers in 3, 2, 1. Okay, y equals kx. That just let's go blue. Y equals kx, so that means they're just proportional to each other. So that's this one here, y equals kx. Y equals k over x, that means they are inversely proportional, which is this one here. That's inversely proportional. That means if the value of x doubles, then the value of y will halve. Okay? Y equals k over x squared. That's this one here. If the value of x doubles, then the value of y is a quarter. You should be able to tell the difference between the inverse and this one here. That's inverse square, we call it. Y equals k over x squared. That's an inverse square relationship, which is very important in physics, as you should know. Y equals root x, or k root x, is this one here. As x gets bigger, y gets bigger, but less than proportionally. Yeah, so you recognize, well, it must be proportional to root x, the square root of x. Things like period of a pendulum or mass on a spring might come up there. This is the important one we're talking about in this video. Y equals a constant to the power of minus x. And you should know that that's this one here. And that is getting towards our exponential function. I'm going to talk a lot about that in this video. Y is a constant to the power of minus x. The exponent or the indice, yes, is x. The fact that it's negative means it's an exponential decay as opposed to an exponential growth. Y equals cos x, and that's obviously some kind of a sinusoidal function. Y equals cos x, y equals sine x is this one here. When you do SHM, you should be familiar with that. Y equals brackets 1 minus k to the minus x, close brackets. That's a kind of a bit of a more complex exponential function. That's maybe like a capacitor charging up. Is that one there. And y equals x squared, yes, is the final one, and that's that one there. So as x gets bigger, y gets bigger, loads. So y is proportional to x squared. Hopefully you got those right. Now, there you go, just checking. Okay, so this is our exponential function. Y equals a constant to the power of minus x. Okay, and there's y, and this should be familiar from radioactive decay. You should recognize the shape of this graph. Do you remember getting the half-life and stuff like that? At A level, we only do decay. We don't do exponential growth. An exponential growth would look like that. Okay, we don't do, there aren't any exponential growths in A-level physics. It's all exponential decays. And the two examples we do are radioactive decay and capacitor discharge. Okay, those are two exponential decays. In OCR, there's actually a couple of other exponential functions as well. I'm going to talk quite a bit. Our example, this one here, n equals n naught e to the minus lambda t. This is for radioactive decay. N naught is the number of atoms you start with, and you'll see that n is then a function of time. Yes, as time passes, the value of n changes. The activity, which I could write dn dt, the activity also goes down exponentially. Yeah, it is a function of time. We'll worry about the capacitors later. So these equations show how a quantity varies with time, and they are exponential decays. In these equations, our constant is this thing little e. Now, what is little e? Little e is a constant. It's 2.718. It's an irrational number. Goes on forever. There's a button on your calculator. I'm sure you know where it is, e to the x. What is so special about this constant? Why 2.718? What's that all about then? Well, don't worry too much about this, by the way, but I need to justify it. If we have this graph of n against time, yeah, and as I said, n might be the number of unstable atoms in a sample of an isotope. And n is n naught e to the minus lambda t, where e is this magical constant. And if we get the gradient of the graph at different points in time, so the gradient of the graph is dn dt, isn't it? The slope. So at a particular point in time, yes, at a particular point in time, we get the slope of the graph dn dt. Now, what we find is that dn dt, the gradient, is proportional to n. dn dt is proportional to, in the case of a decay, minus n, because delta n is negative, because it's getting smaller. So dn dt is proportional, the gradient is proportional to the value of n. And that is only the case, that only happens when the value of the constant is e. Yes? The gradient of the graph is proportional to the value of n. That is actually the definition of your exponential decay, when the rate of change of something is proportional to its magnitude. How quickly the value of n is going down at any point is proportional to the value of n at that point in time. And that only works for a certain value of the constant, and that's little e. Okay, the rate of change of a quantity is proportional to the magnitude of that quantity. That's an exponential decay. This might help you to get your head around that. Imagine you've got 6,000 dice, or is it 6,000 die? I don't know. And you roll them all. Now, what is the most likely number of sixes that you would roll? Yeah, 6,000 dice, roll them all. The most likely number of sixes you would roll would be 1,000, isn't it? Now, what does that number depend on? Yes? Now, 1,000 is like 1 out of 6. What does that number, the 1,000, depend on? Well, it depends on the number of dice. The number of sixes that you roll is proportional to the number of dice. If you then took away those sixes, then it becomes like analogous to radioactive decay. Like if you roll a 6, the dice decays, then what would happen to the value of n as time goes by? Well, because the number of dice that you take away is proportional to the number of dice, yes, then n would go down exponentially. And the number of dice that you take away every throw, and we could call that dn dt, would also go down exponentially. Yeah, the rate of change of n is proportional to n, and the minus sign because it's a decay, because delta n is negative. So radioactive decay as an example, dn dt equals minus a constant times n. Yeah, they are proportional to each other. And then this equation, n equals n naught e to the minus lambda t. Let's talk a bit more about these equations. dn dt is minus lambda n. Well, dn dt, I know I'm repeating myself, but you know, I want to get it stuck in your head. dn dt is the rate of change of n. It's the gradient of the graph. Yeah, dn dt, when I see dn dt, I think gradient. Yeah, the rate of change of n is the gradient of the graph of n against time at any point in time. In the case of radioactive decay, it's the number of atoms which decay every second. Yes, and so that's the activity of the sample. dn dt is the activity of the sample. This thing here, e to the minus lambda t. Now, this is important, and this came to me. I had an epiphany quite a few years ago, and it's really helped me to get my head around this. E to the minus lambda t is the fraction of n that remains after a certain time. Yeah, I'm going to repeat myself. The fraction of n that remains after a certain time. This e to the minus lambda t, at the beginning, when n equals n naught, that equals 1. Then as time goes by, that e to the minus lambda t gets smaller and smaller and smaller and smaller, and it approaches 0. So e to the minus lambda t goes from 1 at the beginning to 0. If you multiplied it by 100, it would tell you the percentage that remains after a certain time. E to the minus lambda t, the fraction of n that remains after a certain time. Okay. Radioactive decay, still talking about that. Now, important, by the way, radioactive decay is random. It's like throwing the dice. If you've got 6,000 dice and you throw them all, are you going to get 1,000 sixes? And the answer is, well, actually, it's a random process. 1,000 would be the most likely number of sixes that you would roll. But unless you've got a very large number of dice, these predictions aren't going to be particularly accurate. Okay, remember that it is a random process, and we're only working out what the probability of the activity will be, the probability of the value of n. But very large numbers are involved, actually. So dn dt is minus lambda n. dn dt is the activity of the sample. It's how many n's, it's the change in n every second, the rate of change of n, the number of atoms that decay every second. Lambda is our constant of proportionality, and we call it the decay constant. So same units on both sides of the equation, the decay constant usually measured in seconds to the minus 1. If the activity is decays per second, or becquerel, then the decay constant is seconds to the minus 1. And it's a property of the isotope. It depends on how unstable the isotope is. Okay, the more unstable the isotope is, then the bigger the decay constant. Yes, and the half-life, you can work out the half-life from the decay constant. I'm sure you know t half is log 2 over lambda. Yeah, log 2 is just, I'm not going to get into natural logs now. It's just a constant, log 2 divided by lambda. N equals n naught e to the minus lambda t. Again, e to the minus lambda t, the fraction remaining after a certain time. As n goes down and dn dt, the activity, is proportional to n, then the activity will go down exponentially as well. So I can write a equals, that should say a equals a naught e to the minus lambda t. And e to the minus lambda t is the fraction remaining after a certain time. I think I've said it about 10 times already. Have a go at this question. Pause the video, pen, paper, calculator. I'll show you the answer in 3, 2, 1. Okay, so the first bit is working out the value of n. Yes, and we know the mass of a mole. Yes, the mass of a mole is 90. We know the mass, so we can work out the number of atoms. Part B is working out the decay constant. Well, I've given you the half-life. Change it to seconds, and then log 2 over lambda. You've got the decay constant. Then dn dt is minus lambda n. The minus here is irrelevant. So dn dt is minus lambda n. 102 times 10 to the 6 becquerel is dn dt. The activity of the sample, that's that. What its activity will be in 40 years. So what I've done is I work out e to the minus lambda t. And that tells me that in 40 years, there will be 0.382 left. There will be 38% left. Yes? And so the activity after 40 years is just 102 megabecquerel times 0.382, which is 39 megabecquerel. Let's talk a bit about capacitors while we're here. So a discharging capacitor, if we look at this circuit up here, you know, if this switch is up there, then the capacitor will charge very, very quickly, very little resistance in the circuit. If you come down here, then the capacitor will discharge. The capacitance is C, the resistance of the circuit here, the discharge circuit, is R. Come down there, the capacitor discharges. Q is the charge on the capacitor, and that goes down exponentially. Yeah, with time it's an exponential decay. The current in the circuit, the discharge circuit, yeah, the current flowing through the resistor, that will also go down exponentially. And the voltage across the capacitor, and in this case the voltage across the resistor, will also go down. Everything goes down exponentially. And e to the minus t over rc. Okay, don't be confused with the radioactive decay. It was to the minus lambda t. Yeah, now basically what's happening here is that our constant, our decay constant, is it's 1 over rc, where r is the capacitance and c is the resistance of the circuit. Apart from that, the value of the constant is different, but the equations are the same form, and everything goes down exponentially, and e to the minus t over rc is the fraction that remains after a certain time. He said it again. Okay, dq dt, now this is our dn dt is proportional to minus n. Dq dt, the rate of change of q, is proportional to q, and the constant, as I said, is 1 over rc. The rc, as you should know, is actually called the time constant of the circuit. It's a property of the circuit. It depends on the capacitance and it depends on the resistance. Rc is the time it takes the charge to fall to about 37%, about 0.37, which happens to be e to the minus 1. If you want to check that on your calculator, e to the minus 1 is about 0.37. Okay, and so dq dt is minus 1 over rc times q, which we can actually write as dq dt is the current, so I equals minus q over rc. Sometimes might be a useful equation, that. Have a go at this question then. You're sat there thinking, oh, this is dead easy, Dave, I can do this. Well, we'll do it then. Have a go at this question here. And I'll show you the answers in 3, 2, 1. There you go. So the charge on the fully charged capacitor is Q equals CV. The initial discharge current is just V over R. I equals V over R. The voltage across the capacitor 10 seconds after the charge begins. I could have asked you to work out the current 10 seconds after. I could have asked you to work out the charge on the capacitor 10 seconds after. What I've done here is I've worked out e to the minus t over rc. Why? Oh, it's not going to say it again, is he? Yes, he is. It's the fraction that remains after a certain time. And in this case, it works out at 0.653, 65.3%. And so the voltage 10 seconds after the discharge begins is 7.84 volts.